Hello everyone, this is already the third part, dedicated to tips for using curves in geometry nodes. If you haven't seen the first two parts yet, you can watch them after this video, since all videos can be viewed in any order. So let's get started right away. And the next section is dedicated to grease pencil's cool features. I think the most attentive ones have already guessed that in order for our viewer node from the previous video to work, we need to place our node tree into the grease pencil object. For this, we take either blank, stroke, or monkey, whatever suits you better. Either option will do. And in such a case, when we create our nodes with Bezier curves, at the very end of the tree, we connect the curve to grease pencil node and switch to edit mode. We see our Bezier handles, which otherwise would not be so easy to see. There is another way, which I will show in future videos. And it's important to note that if we modify the type of these antennae, then their color changes, just like it works in other parts of Blender. Let's say we have two curves. How can we make grease pencil an object that has both a fill, a stroke, and a hole? The most difficult part here is to make the correct fill, and it should be two different materials. Fill separately, outline separately. The fill is done this way. First, we use the fill curve node, convert it back using mesh to curve in face mode, and then we get two separate closed curves. And when we use the fill curve material, we get the result we need. Then we add a regular stroke on top, and there's our filled stroke. If we add a radius node here, we can also change the stroke radius. Note that there are some glitches now, but when we connect the node to the output, everything works correctly. There are only problems in the viewer node. We can connect the radius both pre and post. And by using this factor, we can create such a truly hypnotizing eye. Following this, we will utilize our created hole and position within it, for instance, the pupil of an eye. It's important to note, once again, that this specific problem exclusively occurs with the viewer node. So let's immediately use the output of the tree, the nodes of the tree. Here, I also want to show the feature, how the set grease pencil depth works. He works in such a way that the order in which we connect the geometry to the geometry node matters. If we swap them, we will get this result, no matter how we change the height. The result will be the same anyway. However, if we choose 3D location, we won't be dependent on the order in which geometry is connected to the join geometry node. But then we'll have problems with the outline, so we'll have to shift the outline a bit. And so, when the position of the pupil is higher and along the z-axis it is lower, we can get various interesting illusions. This same trick with filling works with regular geometric objects as well. We can achieve either this kind of result using a simple cube, or a result like this. And finally, the most important section addresses a subscriber's question. How do we move an object along a curve, paying attention to whether it's going up or down, so that it goes slower when going up and faster when going down? This is done quite simply, and as you see, it works in real time. Let's take a closer look at how this is designed. To get started, we'll need to generate a curve. We simply resample it and shift according to noise. For you, this might be a curve drawn by hand or any other method that seems useful to you. After creating the curve, it is essential to resample it with equal distances between points. Otherwise, a more complex setup would have to be created. And so, what you do is set curve normal Z up. It will help us to ensure that our road will always be straight, because without him, the road will be more unpredictable. And the main feature we need here is the tangent. Let's temporarily make the curve with fewer points. Let's say right now we have 24 points, and let's see how our tangents are arranged. If we consider a pure tangent, then this tangent along the curve. We only need the Z component to understand when the curve is moving up and when it is moving down. And when we take only Z, it turns out that the vectors are not normalized. This exact length will help us understand when the car is braking and when it is accelerating. As you can see, here we take the curve tangent and take its Z component, and note that when the arrow points upwards, meaning it is at its maximum positive value, that is when we are going uphill. It is negative when we are going downhill. When we have some kind of gentle slope, whether it's on a mountain or at the base of a mountain, we have Z component tends to 0. And it's on this graph that we define speeds for various path segments. For positive Z, the speed will be low. For negative Z, the speed will be high. And so each point acquires its own sort of weight. Let's reduce the number of points again. And so we see when the little car drives uphill, our speed is very low, it's only 800s. But when it drives downhill, on the contrary, it's quite high, 8700s. Now we see it here too, and now we take these values and accumulate them using the accumulate field node. So, for the first index, that is, for the beginning of the curve, we will have a value close to 0. And the further we go, the more we add all the values together. And in the last node, we will have the sum of all these values. Here we can see that 14.107 is the sum of all values. Output trailing shifts all values by 1. That is, for the first point, we will have 0. And its value will already be at the second point. Thus, if we take this value and divide it by the sum of all values, we will obtain a factor ranging from near 0 to 1. And if we take this other value, we will have a factor from 0 up to almost 1. Therefore, we mix these two values. And what we get is precisely the interval from 0 to 1. Let's take a look at this on the graph. And now, this is precisely how our schedule looks. If we were to connect a standard factor here, it would be linear, and the car would move linearly. But when we use our graph, the car starts to move non-linearly, and this way, of course, the graph looks more accurate. Now, to turn this graph into the position of our car, we need two sample curve nodes. In the first node, we supply our linear animation as a factor. We have here frames from 0 to 240 are converted to a value from 0 to 1, that is, a normal linear factor. And for the input attribute, we pass the modified values of the factor, and in the second node, we take the same curve and feed our transformed factor into the factor. In this way, our position changes depending on whether the car goes uphill or downhill. What we are simply observing right here, the simple little car that we have constructed, and through a standard transform node, we then pass it along. Of course, there could be several little cars, but in that situation, our node graph will be a bit more complex. Here, we use position for position, and tangent and normal are converted into the rotation of our car. Here we just do clear the way. Here we are making trails using the method that was shown at the beginning of the previous video. And here we have such a result. And if we want even more extreme values, we can change the curve. You can find out the values for this curve if you download the file. Here is the third video of this series, and it's not over yet. I have many more ideas. For example, some of these tips can be turned into full-fledged assets and even developed into a set of 2D curve Boolean assets. It is possible to create a node that will display Bezier curve handles not only for grease pencil, but also for any object, and much more. Feel free to send your questions and suggestions. I will try to make a video on this topic, and thanks to everyone for watching.